Okay, test, test. Can you hear me?
Yes, can hear you.
Good, good.
Yes.
Okay, cool. Jacob, I got your email, and I responded to you. I don't know if you saw it, but
Yes, I just responded back. I looked at the course you had already created. I think you've already created the course. I just need to know how the students pay for it when everything. You gave me the course code. There is an option to build institution. I just don't know how to use it.
okay. Let me see. First, let me find the course. Oh, okay. I must have set this up a while ago.
Yeah.
Now, when I set it up, I'm trying to remember because we always, the students purchase it either directly or using these access cards. There's an option to bill institution.
Yes, if you go to edit class settings, I figured this out a little bit.
Okay.
And then there's billing and resources and bill institution. I just don't know how to go from there, but I think this is something I need to find out from the school at this point, how they want to do that.
It's set to student access codes. If I change it to bill institution payment method, I have a purchase order or other, and bill institution contact info. Okay, so when you're there, I don't know if you've done this yet. If you switch under billing and resources, if you switch the radio button to bill institution, and then you select if you have a purchase order ready to go or other, and you put in some contact information, and I guess they'll get in touch.
Yeah. I just need to find out from my institution who to actually put down as to get the bill. So.
Okay.
But yeah.
Well, good. So I don't have to do anything then.
Yeah, I was getting really confused. I figured I would email you and email my dean just to be like, okay, how do I do this? And I found the solution about 10 minutes later.
Okay. And, I didn't know about this, and that may be useful because we have University of Saskatoon is doing the labs, but there are different rules with Canadians. They don't want Canadians using credit cards on web-assigned companies because of the Patriot Act. I don't know the details.
Yeah.
But this may be an option that works for them.
So.
Okay. Let's see here. It's noon, and let me get out of this. And before diving in, I figured I'd show you our new graphing interface. It's almost ready to go. So here the screen. Okay, so this is the existing graphing interface that we've been using for about a decade. It's Flash-based, which is no good. And just as a kind of an introductory project with one of my young programmers, I said, rebuild this. And I think it's some type of JavaScript. Or, no, sorry, AngularJS. I'm not actually sure what he's using. He's whatever my programmers recommended, but not Flash-based. So we've seen this a couple of times. I'll just briefly show you the new one. And we may, tweak a little bit. Maybe put a background color in there. I don't know, but it has all the same functionality. It's not Flash-based, and so you can, add curves if you want. Type in some data to go with it, I guess. And you can also copy and paste into this one, which you couldn't in the Flash-based one, so that's kind of nice. And if you want magnitude scale, that just flips things right there. And you can add information to the title, and it fills in automatically. Or you can label the axes however you want, and save the chart to an image to upload into WebAssign. That's the standard line feature. And for the moon fitting that we saw in Lab 3, all that's there, and it's a little finer grained adjustments than before, so that's nice. And let's see, there's that Venus exercise where you plot the angular size of Venus on this axis and the phase on this axis. And we actually went through the rederivation of this region of acceptability for Ptolemaic models and came up with the same thing that we did 10 years ago, so I felt good about that. And then there's a scatter plot that we'll see not in this lab, but in Lab 6 for plotting the top-down distribution of globular clusters in the galaxy. And finally, another plotting thing that we use in the Hubble Law Lab. So it's all here, and it's not Flash-based. So that should last us for some time moving forward. And it's just on this personal website now, but we'll probably swap it over in a few days.
What's it based on again? It's not Flash.
It's not Flash. It's probably AngularJS. A lot, the Skynet website stuff and the new Afterglow is AngularJS, so I imagine he's doing the same thing here. I haven't talked with my programmers, and they figured that stuff out, me out of the loop. So, okay, that's that. Moving on to the lab. Today we're doing Lab 5. And let's see, there will be we'll meet next week for Lab 6. The week after that, I won't be here, so we'll have a week off. But let me bring up Lab 5. This is the second of the Cosmic Distance Ladder labs. Last week was Lab 4, Parallax, and where we did Earth baseline parallax in the solar system, and then stellar parallax, which at least pre-Gaia gets you out to about half a kiloparsec. Post-Gaia gets you much farther out. And but that it only gets you out so far, so then you swap over to standard candles, and the lab will focus on our Lyraes on Milky Way scales, Cepheids out to the nearby galaxies, and Type 1a supernovae. Then we'll have follow-up labs, like next week, Lab 6, we'll redo the Great Debate, the Curtis-Shapley debate of 1920, which makes use of our Lyraes and Cepheids. And later on, we'll do a lab on Hubble's law, which the Type 1a supernovae would come back around. So this is setting the stage for some other labs as well. Standard stuff at the beginning, of course, the link with the TA giving a pre-lab talk that may or may not be useful. But again, the important bit is right down here, what the students need to observe for the next lab. Again, Lab 6 is that great debate lab, the Curtis-Shapley debate. And the observations here are pretty straightforward. They're going to observe some spiral nebulae. That's, of course, what they were called before we realize they were galaxies like our own. And we can just pop over to Lab 6 real quick. but this is very straightforward. There are no new skills required here. Observe spiral nebulae with skynets, and so there are a list of 5 of them. Any given time of year, probably 3 of them are doable, so they shouldn't panic if they can't get all 5. It's all in the high-through filter. It's all 80 seconds. It's all single exposure, so we don't eat up too much telescope time because these are longer exposures than solar system objects. And they just put them in, during Lab 5 to guarantee they'll be ready by the time they do Lab 6. And it's just, pictures of galaxies, nothing fancy. So I won't go through the process of putting those into Skynet. You've seen that kind of thing multiple times now. Okay, don't need this. Back to Lab 5. Okay, so let's scroll on down to the goals. And kind of, as I've already said, the goal is to use our Lyrae variable stars to measure distances to objects within the Milky Way galaxy, use Cepheids to measure distances to nearby galaxies, and use Type 1a to measure distances to faraway galaxies. So again, it's like the last lab with parallax where we had repetition, but good reinforcing repetition. We're going to have the same thing here. All 3 of these are standard candles, and so they're going to go through this process 3 times. But we have some background information, and this lab has a little bit more than the others because it is setting up other labs as well. So let me go through that kind of quickly. Again, computer is just, or the equipment is just the computer. So background sections on what a magnitude is, what standard candles are, and then on these types of standard candles, the variable stars and the supernovae. So magnitudes, just start with basic stuff. And again, I always feel silly explaining background sections to you all because you all know this stuff, but I'll just do a quick run through so you get a feel for what you might present to students. Here you're introducing apparent magnitudes. In this kind of lab, you do have to make a distinction between apparent and absolute. Here I say that, if just say magnitude by itself, it really means apparent magnitude. And also you'll see throughout the lab, almost everywhere I'm talking about apparent magnitudes, I write in parentheses, think brightness. And everywhere I talk about absolute magnitudes, I write in parentheses, think luminosity. And you'll see I try to just reinforce that over and over because they have familiarity with brightnesses and luminosities, and but these magnitude terms will be new to many of them. And I just give them some examples, like how this was based on an ancient Greek naked eye system, and it's been reinvented as a reverse logarithmic system in the interest of being historically consistent on the interest of what would be most straightforward. But I give them some examples of different limits that can be reached under different circumstances.
Have they seen the concept of magnitudes already? By this point?
Not in the lab course.
So, but they've seen the 2.5 log thing?
In lecture course, yes. I brought that up in the lecture course, but in the lab course, we haven't done any photometry yet.
And do you do the distance modulus equation before this? So
nope. So that will be introduced down here under standard.
Okay.
Yep.
Yeah.
So I'm first just starting on the basic, this
sure.
magnitude here, example magnitudes. It's a backward system. It's a powers of 10 system. And then we go through just a little practice. So there are a few points in this background section because all the rest of the lab is going to be batch photometry. And there's the opportunity that they go through the steps and not really know what's going on. So we're going to just do manual photometry of a single star so they can understand the calibration process. Again, calibration is the hardest thing to explain, but it's also the most important thing, just in general in science with young students. So we're going to switch over to Afterglow and bring up this image here. This is a finder chart, and we want to know the magnitude of star A, and we have a reference magnitude here as well. Now, you got to explain to the students that every time an image is taken, you can get different numbers of photons, different brightnesses, just because of maybe how much atmosphere you're looking through. Maybe they're thin clouds, they're blocking some of it. So any magnitude that you measure off of an image is relative. You take the same picture the next night, and make that measurement again, you get a different magnitude. So you always have to tie it to a reference star, a star of known magnitude. So let's switch over to Afterglow, and we'll just walk through this simple background exercise.
Hey Dan, before you keep going on that, I had a quick question on that distance modulus equation you used.
Yeah, you saw that it was different?
Yes.
So yeah, I'll hop down. And so this is something I just learned from experience. We all know it as 10 to the m minus m over 5. But I found that students often will have a plethora of different calculator errors with that. They'll do 10 to the m minus m whole thing divided by 5, or 10 to the m quantity and then minus m divided by 5, all sorts of things. So I simplified a little bit by doing the 10 to the 1/5 myself. And that's the 1.585. So all they have to do is 1.585 to the difference of the magnitudes. That's why that's different. I never planned on it, but after running the lab a couple times, again, we do this as a giant survey course. 1 in 5 UNC students take the course. Not all of them are mathematically strong. And these are, mathematical labs. They're challenging. It's not like, let's look at pretty pictures and call it a day. So I try to ease the journey for them wherever I can find places to do that.
Thank you.
Okay. Let's just do this quick example. Password. Okay, so let's open this image. Sample 101 lab, standard candle. It's in the directory CD47. And this is a standard calibration field. It's a V-band observation and a little galaxy here. And if you look at the finder chart, I've indicated this one right here is the reference star, and this one down here, star A. Well, this one down here is star A. So they can go back and forth with the reference, and we ask them to, using the finder chart, measure the magnitude of star A and the magnitude of the reference star. So photometry is quite simple. It's aperture photometry. And so for star A, it has autocentroiding, so you don't have to be perfect. And you click, and you get a magnitude there. And just so you can see it better, I'll zoom in. And if you go off and back, it resizes the aperture and the annulus. So again, aperture photometry, it's counting everything in the red circle, and it's using the data in the blue, between the red and blue circles to come up with the background level. And these algorithms are straight out of IRAF. So they're gold standard stuff. You could publish with it if you wanted to.
I was just curious, do you use the modal in the background ring to eliminate problems like that star that's in it?
I'm pretty sure it's the mode.
Yeah, okay.
It could be the median. It's whatever IRAF uses standard.
Yeah, okay.
Now, I just did a paper on outlier rejection, so I've spent a lot of time thinking about this, to reject the crap in there, because there are all sorts of things you can do it that's better than sigma clipping.
Yeah, I remember that paper. You talked about that at the Skynet meeting.
Yeah, so I'm hoping to build some of that into new Afterglow as options as well. It's particularly useful in the radio because the stars are not so sharp, and you have larger regions that are contaminated within the annulus. So we're hoping to add some of those advanced features, but this right now is IRAF standard. Okay. Anyway, so we got the two magnitudes here, 13 for star A, 11.28 for the reference star. And let's see, here we stick those two things in here, and then we tell them the reference star is really 12.01. So they calculate a correction constant, just the 12.01 minus what they measured, that 11.28. And so it's a difference of 0.73. And then to calibrate everything else, like their star A, you just add the 0.73. So they measured 13, but it's low because the reference star was low by 0.73. That one's low by 0.73. They added on, and then they have a calibrated magnitude for their star. Again, students have the hardest time understanding calibration, why it's necessary, but you all understand the importance. This is an attempt to help them understand it a little bit better by going through it in a manual sense before we just start using batch photometry tools where it's all kind of mostly done for them.
Yeah.
Okay. And continuing on with the background, the next background section is standard candles. And again, I emphasize distance is the hardest thing to measure in astronomy. You can't just see distance. Here's that same example where two stars appear to be the same brightness, but they're really different luminosities and different distances away. And they're all familiar with this equation. Brightness is luminosity over 4 pi distance squared, which you can flip it around and solve for distance. Where the idea is if you know the luminosity, that's the big if, you can measure the brightness, just what you see, right? That's what you're doing with photometry in your image. You're measuring brightnesses. So if you knew the luminosity, you could calculate the distance. And to really drive home the concept of, many of them will confuse brightness and luminosity. So I compare it to a light bulb. A 60-watt light bulb is always 60 watts, no matter how close it is to you or far away. But brightness is how bright it appears. So tie it to something really familiar like a light bulb of known wattage. Anyway, then we switch over to this equation. And so we've already introduced the idea of magnitude. Instead of brightnesses, astronomers talk in magnitudes. And those are apparent magnitudes. And instead of luminosities, we talk about absolute magnitudes. And I don't know if I even get into the technical definition here. I do in the lecture course, but here it's not really necessary. You know, it's the apparent magnitude it would have if you moved it to 10 parsecs.
One tiny comment. You might want to migrate eventually to lumens for your light bulbs. Wattage is out of the, it's irrelevant now with LEDs and all of that. So yeah, all light bulbs, or properly called lamps, are now labeled with the lumens.
Okay. Good to know. It's making me feel old here. So, all right. And as you know, I am going to be doing a major go-through cleanup of everything over the summer. So I'll try to remember to do that. And you know, if you're using these things and you see things that I forgot to do or I did incorrectly, just always send those suggestions to me, and best by email, and then they're more likely to be accomplished. But I made a note of that. Anyway, so here I'm driving home the definitions of the kind of qualitative definitions of apparent and absolute magnitude. It's brightness and luminosity, essentially. They're equivalents. And this equation here that they understood becomes this equation in these new units. So that's kind of the simple way I present it without any derivation. And where little m is the apparent magnitude and capital M is the absolute. Okay. And so in this lab, it says what we're going to do. It kind of sets it up here for 2 variable stars and exploding stars. For each one, we're going to first confirm that it's a standard candle. So, you know, regular stars, they have a wide variety of luminosities. It could be 10,000 times more luminous than the sun, or 1/10,000th the luminosity of the sun. So just any old star doesn't count. But there are special types of stars, such as variable stars, or some types of variable stars, some types of exploding stars. If you can identify it as that special object, you know its luminosity. So the steps are: confirm that it is a standard candle, that special type of object. Then use the knowledge of its absolute magnitude, think luminosity, and then measure its apparent magnitude, think brightness, and then calculate its distance. So those are the 4 steps over and over. But 2 more background sections before we dive in, one on the variable stars, and then one on the supernova. So the variable stars we're using are Lyraes and Cepheids, and the kind of, in class, I explain them in great detail, especially in Astro 102, because we're into Astro 102 material now. But here in the lab, that can be done by people, you know, from Astro 101 or whatnot. I try to keep it really simple. I describe them as kind of stably unstable stars. They're outer layers. We all know it's an opacity effect, where the opacity gets high, and so it's trapping light and energy, so it inflates and gets big. The density drops, the opacity drops, the light escapes, and so it comes, you know, shrinks back down, and as it shrinks down, the opacity changes again, and it cycles through over and over again. And I don't know if you have to go into that much of an explanation. It depends on the level of your students. But it kind of a very, very simple statement is they're stably unstable stars. They expand and contract over and over again. And our Lyraes, they have periods less than a day, and the Cepheids have periods more than a day. That's the simple way to divide it. Of course, there are different types of Cepheids and also types of variable stars, but I'm not going to go into the distinction between Cepheid type 1, Cepheid type 2. Just this is the one that can be used as a handle, and keep it simple. And so what we've done, just tying it back to the previous lab, and again, the concept of calibration, which is difficult, using parallax, we got far enough out to find a few Cepheids and a few Lyraes. And since we knew their distance, measured their brightness, we calculated their luminosity and learned, oh, all Lyraes have the same luminosity. All Cepheids have a luminosity tied to their period. So you measure the period, you can get luminosity. And hence, we can flip that around in the future. Once we identify it as one of these, we know its luminosity and then can work it backwards. And in reality, there is this intermediate step of spectroscopic parallax, because parallax only got us far enough out for 1 or 2 Lyraes and Cepheids. But now the guy is out there, it's going out far enough, and there is no gap really anymore. So I don't talk about spectroscopic parallax. I had to condense the cosmic distance ladder down to fit it in. So I kind of skipped that step, and now the guy is caught up with my simplified story that everything's good. But anyway, with the Lyraes, we learned that they all have an absolute magnitude luminosity of about 0.75. And with the Cepheids, it's connected to the period. There's a relationship here, and I give them an equation for that. They can measure the period. They don't even have to know what a logarithm is. They just have to press the button on the calculator. They can get the absolute magnitude using this equation. So with Cepheids, there's that extra step. Let's do the extra. For both of them, you have to measure the period. To confirm that the Lyrae is the Lyrae, it has to have a period less than a day. If it's more than a day, it's a Cepheid, and you then use that period to come up with the luminosity. I point out it's base 10. Okay, and then the last bit, the type 1a supernovae. Again, there are different types of supernova, but you can break them down very roughly into type 1 and type 2. And technically, it's 1As. We know there are also 1Bs and 1Cs, but they're more like type 2. Those are all giant core collapse. With type 1A, it's carbon detonation. You have 2 stars in close proximity. Again, I know you know this. I'm just example background presentation. A 1 star, it's more massive. It goes through its evolution first, becomes a white dwarf. The second star is lower mass. It later on goes through its evolution, becomes a giant. If they're in close proximity, you get mass transfer onto the white dwarf. Its mass increases. If you want to be technical, it forms a layer on the surface that builds up, gets hot, and ignites, and you have a little flash called a nova. But it just burns hydrogen to helium on the surface, and most of the mass is still there. The stream reforms, more comes over. Nova, nova, nova. These novas happen every timescale of decades, depending on the proximity. But slowly over time, you're building up the mass. White dwarfs start around 0.6. Once you get to 1.4, they change your sacred mass. It can't hold itself up anymore. It begins to collapse. Misconception is it collapses to form a neutron star. That's not the case. If it were made of iron, that would be the case. But as it collapses, it heats up. It's made of carbon, for the most part, with a helium layer. It hits that carbon ignition temperature, and then it explodes. And even that's simple because there are huge debates. Does it detonate or does it deflagrate? Is it slow burning? Is it explosive? How do you have partial burning, full burning? But that's all details that way beyond the level of this. You just say it explodes, and that's why they're standard candles. You're always burning 1.4 solar masses. It's always the same amount of fuel, and so it's a standard candle, common luminosity. There are, of course, subtleties with the position and brightness of the peak of the light curve, but you don't have to get into that. Anyway, here's the simple test here. Type 1As, they get bright and they fade. Type 2s, which are the massive star blowing up, you have a plateau phase. So if you can ID a supernova, you plot the light curve, you determine which you have. If it's a type 1A, then you can use it as a standard candle. And they all have an absolute magnitude of minus 19.3, and this is from, we found nearby ones in galaxies that we knew the distance due to Cepheids. And so we could figure out their absolute magnitude and learn they're all the same approximately, and then we can use that information to get farther out. Okay, so that's all the background material. Remember, you're setting up background for a number of labs here. Now the actual process of doing it is not that bad. Here's the section on observing. We looked at this last time. You have different globs for different seasons. We're in spring, so we're going to be looking at NGC 3201. Again, you should put in one set for the class, not one for the student. They don't have enough observing time for that, but one set for the class that will then be shared. And right now that sharing can be done by you emailing me or one of my staff, and we can move it into the sample directory. But in Afterglow 2, you'll be able to do that yourself. Okay, and we have finding charts here. And yeah, this is just collecting the data, but you have to indicate which one here. And that sets the auto grading. If they observe one but click the wrong one, everything will be marked wrong when they auto grade. And you have to go back and give them an extension, and they change it and let it auto grade again. Okay, procedure. We have three parts. One's for the globs, one's for the one's for aurolaries in globular clusters, one's for Cepheids in nearby galaxies, one is for type 1a supernova. Again, they only collected the data for the aurolari as a class. The Cepheid, ignoring the Magellanic Clouds, there's really only one galaxy that has one bright enough for us to do this with our small telescopes. Same one Hubble used. At least that's my understanding. And but that one, it's a bright Cepheid, which means it's a long period Cepheid, 60 days. So we're not going to have the students collect that data. That's canned. And the supernovas canned as well and predict when those are going to go. So the thing they're collecting is the aurolari as a class. So let's dive in and look at the aurolari first. I'm going to switch over. There are all the instructions here, what they need to do, but I'll just switch over to Afterglow and explain it. So let's get rid of our sample here, and this is going to be batch photometry. And all of these images have WCS on them, so you're not going to have to go through and do single star alignment or any of that. I'll show you. So under processes, we're down to batch photometry, add files and folders, and this one, it was globular cluster NGC 3201. And here's all the data, just select it all. And sometimes it may take a few seconds to load the headers. Those loaded lightning fast for whatever reason. So they're all here, and we hit next. Okay, it's brought up the first image. I'll fit it. And this is where we're going to use our finder chart. And we're going to click on either the reference star or the aurolari, label it, click on the other, label it, and then use the WCS and find them in all images. So let's see here. Back to our finder chart. So we have this kind of cluster, and it's right above it. So this is the aurolari out here. And then we have a little double. It's probably hard for you to see, but I can see, on your own screen you can see it well. Double with one over that. So I think that's this, yeah. So that is like I said, that's the aurolari here. So I'm going to click on it and type in RRL. This changes the name. Maybe I can make it a little, I can't make my screen bigger on this one. And this one is the reference star. Click on it, typed in REF. And then I'm going to use the WCS and find sources in all images. So now if I go to any other image, it shifted, but it found it. And I can even go like all the way to the end. We've had a meridian flip, and so they're now down here, but marked. So that's the great thing about the WCS. In previous labs, we used single star, multi-star alignment because those were of planetary images with no background stars, so we couldn't use the WCS. That's why they had to do the alignment manually. But these things, we obviously have lots of stars, so they do have WCS applied. And all Skynet images get a WCS attached to them automatically unless it chokes. Okay. So then we found them in all images, and we hit next. And this is a table of our library reference, and all sorts of things, including the magnitudes measured. And you can export this to a CVS file and go into Excel and work if you want. But one of the goals of this lab was to be Excel independent if we wanted to be. Again, this is a broad audience. They may not all be very good at that. That's why we made a graphing application specific to the lab. So we also made a plotting application specific to the lab. It's here under Data Analyzer, and this will be rebuilt in Afterglow 2.0. It's coming up pretty soon, adding that. So we have our two stars. Indicate which one is the variable star here. That's the RRL, as I labeled it. The reference star is ref. And once you have them both, it subtracts them. And remember the manual exercise. We, basically, what we're doing here is RRL minus ref plus actual. And the exercise, what we did is ref minus actual and then added it to the RRL. So when I redo the instructions, I may rephrase this or change the orientation of the buttons to make it go into kind of the exact same process. But it's really the same thing. Again, the difference here, and then you're typing in the actual magnitude of the reference star, which is there in the manual. Looking for it here. And this is the reference star's magnitude, and I've corrected for dust along the line of sight. So 13.6. So we type that in here, 13.6. And as you're typing, it updates the y-axis. So now everything is in calibrated magnitudes. So we did it manually to get an idea of how that works, but now we're doing it in bulk to all the stars at once. Okay, now with our libraries, the period is less than a day. And here we have 1, 2, 3, 4, 5, 6, 7 days of data. So each day you get a little snippet of the cycle. And it's hard to figure out the period just looking at that. So we do period folding. I should point out in the lab down here, there's a tutorial that Aaron Laclouzet did. He was my postdoc and a great educator. So it's much better than all the other tutorials, which are screencasts and videos of my grad. This one's really good. Introduction to period folding. And he starts with the complete period and then takes out the data where it was during the day, takes out data where it was cloudy, and so you end up with kind of this fragmented thing here. Then he explains about how it works. But so we can click on period folding and start guessing. Is it a 0.3 day? No, I don't see the pattern there. 0.4 day. And you can be guessing forever. It's really sensitive. So we've built in a way for the student to be given the period, or at least a very strong hint. And so we're going to change our view from light curve mode to Fourier mode. And they don't need to understand a Fourier transform. It's just a tool. So when you're in Fourier mode, you got to pick a low period, and all the R libraries are less than a day. So let's search between 0.1 and 1 day periods, and then you got to do a step size. Give it enough resolution there. There's 0.01, so maybe 0.001, and all you're looking is for the high point. We have different possible periods here, and this is how likely things landed up. It's actually not a Fourier transform. Fourier transforms require evenly spaced data. This is not evenly spaced, so we use something called Lom-Scargel, which is the same concept. But anyway, you go up here and looking at the numbers, it says 0.562, 0.563. So you want to guess somewhere around there. Go back into light curve mode. We're still in period folding, so 0.562. There we go. Nice and neat. Here it is decreasing, and then it increases again and then repeats. Now normally they plot 2 cycles, and in Afterglow 2.0 we'll plot 2 cycles. It can be confusing because the noise is the same in both cycles, and unless the students know what's going on, they're going to say, why is the second half of the data exactly the same as the first half? but it's convention in these fields to plot 2 cycles. It makes it easier to keep it cyclic. But anyway, this is 1 cycle, so it's going down, brightening, and then starting over. And you can see if you try other things, let's go from 0.56 to 0.57, it's starting to fall apart. So it's really sensitive. Okay, so we have the period. Let's go back to the lab and see what questions it's going to present us with now that we know that. And we're in answer key mode. The students can't see this, but here you can see the folded light curves. And I should say you can collect your own data, or we have samples. And clearly I just pulled up a sample. So either way. Time between peaks and troughs. Actually, let me change this to NGC 3201. That should update the defaults. It didn't, but I guess it would on auto grading. Anyway, you put in the period here. Then the question is this period consistent with being an RLIRE? It's less than a day, so you say yes. If so, what's the star's absolute magnitude? Think luminosity, cap M. And we tell them what resolution to include. And that's 0.75. That's from the background section. All RLIREs are 0.75. So they got the luminosity. Now they need to measure the brightness or the apparent magnitude. And for that, we're taking the average from peak to trough. So going over here, I didn't even realize I have scroll wheel mouse control here. This is the peak. This is the trough. So if we go kind of halfway between them, 0.38, 0.385 maybe. Notice these are magnitudes, so it's going backwards like you'd expect. So bright is high in these plots. So you type in the absolute magnitude here, the apparent magnitude here. Did I put in the right 13 points? Oh yeah, that's right. The default answers are for the other globular until you press the. They don't see the stuff in the green box. Once they submit it, those numbers will update. Anyway, they put in the average magnitude here. They calculate the distance here and show their work using distance modulus equation here. Then they look up the true distance, and it's set up to come out in kiloparsecs. So they look it up in kiloparsecs, which is easy to find. We tell them to use Wikipedia. Calculate percent error. Discuss sources of error. And the sources are difficulty estimating the peak and the trough because it's a little noisy. Also, RLIREs, the absolute magnitude is 0.75, but there's in reality some variation there. Those are the real sources of error. Sometimes they'll blame the photometric technique, the period determination, or dust, diminishing the reference star's magnitude. But you can accept it if you want, but those are not really major sources of error. The photometric technique is, very gold standard. Aperture photometry, it's going to be really accurate. Period determination is super precise, as we saw. And to get the data to fold on top of each other, you can really nail the period. You have to really nail the period or else it won't line up. And I've already dust corrected the reference star's magnitude. Now, if they say I selected the wrong star or did something incorrect, that doesn't count. If you selected the wrong star, go back and select the right star. If you select the wrong star, it's just going to be gibberish. It's going to be random data on your plot. Okay, so that's the RLIRE. Next is the Cepheid. Same deal, except the luminosity depends on the period. And I'm going to walk you through that. But you'll see the repetition here, so we'll get rid of this. Do it again. So process batch photometry. I'm going to go up, and the Cepheid is the nearby galaxy. This one here, 6822. Grab all of the images. Not sure what's in that extra folder, but I don't think I need it. Select. Okay, it's loading the headers, which, again, it happened lightning fast. And I often like to fit to see the whole thing. And here's the reference image. And it's down here. Looking at the Finder chart, this one right here is the reference, and this one right here is the Cepheid. So this is the ref. This is the Ceph. Use WCS, find sources in all images. So now if I click any other one, I'll go to the end. Oh, here it is right there in the middle. So it found them because it used the WCS. Next. Export to data analyzer. Variable source is the Cepheid. Reference source is the reference. The reference star's magnitude is 15.25. Goes here. Set the numbers on the y-axis. And you can see we got most of a period in them a little bit later on. But again, we can fold this. We don't have to guess at it. We go into Fourier mode. And for this, they're all greater than a day. So let's search from 1 to 100 days. It's putting the peak out at 67.5 maybe. Back to light curve, I'm going to period fold 67.5. And again, if I tried something different like 77.5, it's starting to fall apart. There's 87.5. Here you can see that extra data. 67.5 lands it right here. So we know the period. Same process as before with just one extra step. They type in the period. Is it consistent with being a Cepheid? Yes. If so, calculate the absolute magnitude. And that for Cepheids depends on the period. Here's the equation from the background section. They get like -6 or so. Then they put in the average apparent magnitude halfway between the peak and the trough. So about 17 maybe. That goes there. Calculate the distance using this equation. Show their wiki, the true distance. It's about 500 kiloparsecs away. And they should get an error of only a few percent. Sources of error are the same as before. Okay, not to sound like a broken record, but one more time, there's a little twist here as well with the supernova. So now we're going for a faraway galaxy. It's a type 1a, and I'm not going to tell them which one is the supernova. I've given them the reference star and its magnitude, but they have to figure out the supernova, and they can do that by making a movie, which they know how to do. So they grab the supernova images, they'll single star align them. We could WCS align them, but we taught them how to do single star alignment because we did that with planets when there were no background stars, no WCS. So we just tell them to do what they know. Single star align a bunch of images. I won't bore you with that, but I'll just load up the batch photometry. And I'll go to my workspace where I have some pre-aligned images all ready to go. They are these right here, minus these Alpha Centauri ones from before. So these have already been aligned. I'm loading them in now. And oh, I'm sorry, I'm in batch photometry, not yet. But I'm making a movie. So I aligned them and I'm making a movie so we can figure out which one is the supernova. It will fade away. Then I'll batch photometer once I know what the supernova is. Done a little bit, loading the aligned images into the movie maker. Select, next. Again, you press the play button because it will take a second to get all the images in there, like it just repeated it. Okay, we have them all in there. Now, in the lab, we give some suggestions for histogram settings to make it a little bit easier. If you're in Z-scale, everything is bright and apparent. I'm going to stop the movie. I'm going to bring up the histogram, and we recommended 99.99 and equalize to all the images, and now I'm going to play it. And the students will often ask about the little dots bouncing all over the place. They're just cosmic ray hits. They're to ignore that. And you can give them a hint, like here's our reference star right here. Give them a hint. The supernova is kind of close to the galaxy, and you've probably picked it out here. Fading away and gone, and now the movie's restarted. It got bright, now it's fading away. There was a cosmic ray over there. So by making the movie, they can figure out, I know the reference, now I know the supernova. And again, our movie saving isn't working, but at least they know the supernova. So now we go to batch photometry. I'm going to add these files back in, minus those 2 Alpha Centauris we don't need. Okay, this is my reference star, REF. This is my supernova, SN. Use WCS, find sources in all images. Check another image, yep, still marked. Go to next. I got my data, which I'm going to go straight to the data analyzer. The variable source is the supernova. The reference source is the ref. And then I got to type in the reference source magnitude, 14.39. So everything's calibrated now. In this one, we don't have to do any period folding. We have to recognize the shape, and this is the shape of a type 1A, no plateau. And we're going to need the peak. The peak's around 14.6. So again, back to the lab. And this is right at the end here. Those are all the instructions and words that I just said. Here's the answer key. And is the light curve consistent with being a type 1A? Yes. If so, what's its cap M? And from the background section, all type 1As are negative 19.3 with a little bit of uncertainty. Estimate the peak magnitude. Once we calibrated, we saw that was 14.6. Calculate the distance and show your work using the distance equation. We give them the true distance to this galaxy. It's 56,000 kiloparsecs. They calculate a percent error. It should be, around 5 to 10, something like that. And then there's standard sources of error. Difficult determining the peak because there's a little bit fuzzy. And all type 1As are not exactly minus 19.3. There's some variation. Now, of course, the supernova Hubble-Sconson people, they very carefully measure that variation. The differences in the brightness are tied to the lag of the peak, but that's more advanced than for this course. So we'll just leave it, at that level in this exercise. And that's it for Lab 5. So Lab 4 was parallax, repetition, getting farther out as we went. Now this is standard candles, repetition, getting farther out as we went. And now we'll take a break before pushing farther out and do some stuff with this. We'll do the Great Debate, and then we'll have a separate lab on the Milky Way about building up its rotation curve in the middle, in the radio, and measuring its mass before hopping back on the cosmic distance ladder with Hubble's law. That's that. Questions?
Just one question, Dan. Are you on a semester system or a quarter system?
We are on a semester system.
Okay, good. Thanks.
Yep. And again, it's here at UNC, we do 101 one semester, 102 another semester. And some people don't go on to the second, but they get a feel for some of the stuff in the second through the lab course. Some institutions do it all in one semester, in which case this lab pairs nicely. It's a lot of information to do it all in one semester. Or you can take this lab and do it over a year, and the returning students, it's still there for them. They come back, and the first semester they do half the labs, second semester they do the other half. So all sorts of ways to put it together. Quarters, I haven't thought about the ideal combinations, but I'm sure there are ways to do it. Anything else? Okay. Next week will be the Great Debate, which ties very tightly into this lab we just did. And then we'll take a break. because I'm going to a radio observatory, and then the next week we'll do some radio astronomy with Lab 7. See y'all later.
All right, thanks.
Thank you.